For most of its existence, SpaceX has been guided by a singular, almost mythological ambition to make humanity multiplanetary by colonizing Mars. Yet in recent years, the company's operational priorities have shifted in ways that reveal how complicated the gap between vision and reality can be. As SpaceX deepens its commitment to NASA's Artemis program and the lunar economy, questions naturally arise about what this means for the Mars dream, and about whether Mars colonization, even under the most optimistic scenarios, is as near as its advocates have long claimed. SpaceX's pivot toward the moon is not a repudiation of Mars, so much as a recognition of where the near-term money and missions lie. NASA's Artemis program, which aims to return humans to the lunar surface for the first time since 1972, selected SpaceX's Starship as its human landing system, HLS. This was a landmark contract worth billions of dollars, and it anchored SpaceX's most powerful rocket to the moon's gravity well for at least the near future. The logic of this pivot makes obvious sense. The moon is roughly 240,000 miles from Earth. Mars, at its closest, is about 140 times farther. The communication delay to the moon is just over a second. To Mars, it can range from 3 to 22 minutes. Supply missions to the moon take days, to Mars, months. In almost every operational dimension, the moon is a more tractable destination. It offers SpaceX a proving ground for the very technologies, life support, in-situ resource utilization, long-duration surface operations, that any Mars mission would require. The lunar program is, in this sense, less a detour from Mars than a dress rehearsal for it. There is also a commercial dimension that is hard to ignore. A nascent lunar economy is emerging around the Artemis framework, with private companies competing for contracts in communications, logistics, and resource extraction. SpaceX, by positioning Starship as the workhorse of this economy, is planting a flag in territory that is likely to generate revenue on a timescale relevant to the company's financial planning. Mars, by contrast, offers no near-term commercial return whatsoever. The challenges of establishing a human presence on Mars are so numerous and so severe that it is worth examining them with some care, because the public discourse around Mars colonization has sometimes treated them as engineering problems awaiting obvious solutions, when in fact, many of them are open scientific questions with no clear answers. The journey itself is the first obstacle. A crewed mission to Mars under current propulsion technology would take between 6 and 9 months, depending on orbital alignment. During that journey, astronauts would be exposed to cosmic radiation at levels that significantly exceed what we consider safe for long-duration spaceflight. Earth's magnetic field and atmosphere provide substantial protection that simply does not exist in deep space. The cumulative radiation exposure over a round trip, assuming a surface stay of several hundred days to wait for the next viable launch window, raises the lifetime cancer risk of crew members to levels that would be difficult to accept under any existing regulatory framework. SpaceX and others have proposed solutions such as water shielding and storm shelters, but none of these has been validated over the full duration of a Mars mission. Then there is the Martian environment itself. The atmosphere is roughly 1% as dense as Earth's, and composed almost entirely of carbon dioxide, which means it offers little protection from radiation and no breathable air. Surface temperatures average around -60 degrees Celsius, with swings ranging from 20 degrees above zero at the equator to -125 at the poles. Dust storms can envelop the entire planet for months at a time, blanketing solar panels and grinding equipment. The planet has no global magnetic field to speak of, meaning the surface is perpetually bathed in solar and cosmic radiation. Gravity deserves special mention. Mars has about 38% of Earth's gravitational pull. While this is more than the Moon's 16%, it is far less than what human physiology evolved to handle. We know from studying astronauts aboard the International Space Station that prolonged microgravity causes bone density loss, muscle atrophy, cardiovascular changes, fluid shifts toward the head, and visual impairment caused by increased intracranial pressure. What long-term exposure to Martian gravity, not zero-G, but reduced G, does to the human body is simply unknown. If it turns out that the human body cannot adapt to 0.38 G over years or decades, the entire premise of a self-sustaining Martian colony collapses. Children born on Mars might be unable to survive a return to Earth, or might themselves suffer developmental consequences we cannot yet predict. Sustaining a colony requires food, water, and breathable air. Water ice exists on Mars, primarily at the poles and in the shallow subsurface at higher latitudes, and can theoretically be extracted and electrolyzed into hydrogen and oxygen. Carbon dioxide can be processed using the Sabatier reaction or similar chemistry to produce methane fuel and water. Growing food in Martian soil presents its own complications. The regolith contains perchlorates, which are toxic to humans, and lacks the organic matter and microbial life that makes Earth's soil productive. Greenhouses would need to be pressurized, heated, and shielded from radiation. All of this is technically possible in the way that many things are technically possible. It would require enormous ongoing energy inputs and infrastructure whose failure modes are life-threatening. Musk has argued that a self-sustaining Martian city would require roughly 1 million people to maintain the kind of industrial and technical civilization that could survive without resupply from Earth. Getting there would require thousands of Starship flights over a period of decades. An astounding logistical undertaking, even if each flight proceeds flawlessly. But the deeper challenge is not merely one of transportation. A self-sufficient Mars colony would need to locally produce everything from semiconductors to medical equipment to construction materials to spare parts for its own machinery. It would need engineers, physicians, farmers, chemists, electricians, and specialists of every variety. It would need political institutions, legal systems, and social structures capable of maintaining order and cooperation under conditions of extraordinary stress and isolation. The history of isolated human communities on Earth, Antarctic stations, submarine crews, remote island populations, does not inspire unlimited confidence in our ability to sustain cohesive social functioning under prolonged confinement. And unlike those communities, a Martian colony would face the possibility of catastrophic, civilization-ending failure if a key system, life support, power generation, food production, were to fail faster than it could be repaired. None of this is to say that Mars colonization is impossible or unworthy of pursuit. The case for it ultimately rests on an argument about civilizational risk, that a species confined to a single planet is vulnerable to extinction in a way that a multiplanetary species is not. Asteroid impacts, pandemics, nuclear war, or climate catastrophe could, in the most extreme scenarios, threaten human survival. Establishing a second home, however harsh, is insurance against that risk. There is also a scientific case. Mars likely once had liquid water and may have harbored microbial life. Understanding whether life arose independently on Mars and what became of it is one of the most important questions in the history of science, with implications for our understanding of life's prevalence in the universe. A permanent human presence on Mars would accelerate that inquiry immeasurably. And there is the simple matter of aspiration. The Apollo program, undertaken in an era of political competition and technological heroism, produced scientific knowledge, engineering advances, and cultural inspiration whose value is difficult to quantify, but impossible to deny. A serious commitment to Mars, even if it takes a century to bear fruit, might produce similar dividends.